Cool. So thanks for coming back for my lecture. I hope you're not very sleepy after lunch. All right. So today, what's the plan? I have a lot of things to tell you today for the second part of the lectures, because the idea is to show you that quantum cryptography is so much more than just QKD. But I still have some stuff left on QKD that I wanted to tell you, so I will start with that, and then we look at like other protocols that, like a couple of other protocols that is there and they're important, so I'm going to cover them. And then the last 2 points of the talk is where I introduce you that there are other assumptions based on which you can also do cryptography, and you can combine them with quantum cryptography, and it leads to very interesting results. So these are more things that I will tell you so that you get some idea of that where are the areas of research these days on these topics. Okay. Everyone good with the plan? Let's go. So if you remember, yesterday we covered QKD. Just a quick recap, it was you were sending states in bases Z or X, and you were sending like these individual states, and then Bob was measuring, and then you were like checking all the bases, then all that. And I showed you a proof of how that works, but then I told you that there's also like some problems with the proof, or it can be improved. So I'm going to talk about that. But before I talk about how we do the proof, I need to introduce you another version of QKD. So first of all, there are many versions of QKD. There's not only one. The one you saw was BB84. It was with Bennett and Brassard. But there are some QKD protocols that instead of 4 states, you use 6 states. There's some versions that you use only 2 states, and there are like variants. The one that I want to talk about today is the one that uses entanglement. So the entanglement that you saw before, we're going to use that, and we're going to now do another version of protocol. Another point is that there is a big part of quantum cryptography where you also don't want to trust the devices. So in the protocol that I showed you before, you have to trust that. So Alice and Bob are your trusted parties. So you have to trust that the measurement device will do what the measurement device is supposed to do, and the preparation will do what the preparation device is supposed to do. So you kind of like need to have trust on your devices. But there are versions of QKD where people want to remove that assumption, and this is possible by using quantum information. This part is called device-independent protocols, or device-independent QKDs. These are very nice and interesting, but I'm not going to talk about them today because it's a field on its own. Just for you to know that this exists. Okay, so let's get to the entangled-based protocol. The setup is the same. There's Alice and Bob, and now they share n copies of maximally mixed state, right? The EPR state. So the state is the one that you saw in the previous lecture, where you have this. 0, 0 plus 1, 1. So you need n of them, right? So you prepare one copy, another one, So you need n of this, n copies of this, because you're going to use one of these per each bit for your key, and you're going to see why. So the way it works is very simple. Alice, you remember Alice was choosing 2 bits, one for her bases and the other one for the bits that was encoding, right? This time, Alice only chooses 1 bit, right? She chooses 1 bit, and that corresponds to a basis, same as before. So it's either X basis or Z basis. And then she measures her part of the entangled state. So if you remember from the previous lecture, this is a 2-party state, right? So Alice has a subsystem, which, as we saw, it's a maximally mixed state. But basically, this protocol is on Alice's side. This qubit is on Alice's side. This qubit is on Bob's side. This qubit on Alice's side. This qubit on Bob's side. So Alice has a qubit system on her side. Bob has one on his side. And they're far apart, and the state is entangled, right? So Alice chooses that bit and measures her part of the state. Then she's going to get a bit as a measurement outcome. That bit is going to be A, right? So if A is 0, I conclude that I have a state 0 or plus. If A is 1, I conclude that I have a state 1 or minus. Almost similar to the previous. And then Bob will do the same thing. So the only difference is that Alice will do the measurement. Now this measurement of Alice will change the entangled state. So now when Bob does the measurement, he's going to measure something that has been affected by Alice's measurement. So he's going to pick, again, a bit, and that bit corresponds to a basis, X or Z, and he measures, he also gets a bit, right? So now Alice has two pairs. One is her choice of basis. One is the outcome of the measurement. Bob has his choice of the basis and his outcome of the measurement. And the rest is like VB84. So what they do is, again, they both announce the basis. They look at the places where these two matches, where the basis matches. If the bases don't match, you throw away that column. If it matches, you keep that. And then you do everything that I told you. You do privacy amplification, information reconciliation, all that classical post-processing, and you pick some part of it to test if it's there or not. So the rest is like quite similar. The only difference is that before I was sending a state from Alice to Bob. Now they both have a state in the beginning, and then they start to measure. Okay, so why this work? So the first thing you need to remember from yesterday is that I told you that maximally entangled states, they have this property that I can write them in different bases and they still have the same form. They're still maximally entangled and they still have the same form. So now if you write your state in 0 or 1 in Z bases, or you write it in plus minus bases, it has exactly the same form. And so first of all, who believes me that this protocol works and who doesn't? Like who wants me to show you why it works? Why it's correct? Let's forget about the security. You want to see? Okay, so let's say, so we're gonna do one bit just to see how it works, right? So let's say Alice picks, give me a random bit. 1, okay. So 1, then Alice picks X bases, right? And she measures, right? Because I can write that in terms of plus and minus, then I can easily see that when I measure on the X bases, right, with probability half, I get either plus or minus. Let's say I measure, and I get plus, right? So now my pairs of bits are 1, so A is 1, which is my basis, and 0, which is my outcome, okay? But this doesn't end here, right? Because this was an entangled state, and I have done a measurement, something happens because of quantum mechanics, and that is collapse, right? So what happens is that now I make that a state collapsing into the state of plus on Alice's side and plus on Bob's side, right? So now if Bob, let's assume the case where Bob has the same random bit. So Bob flips a coin, and by chance, this is also 1. So now Bob will also measure his own qubit in the X basis. And when the bases match, because it already collapsed to plus, then the measurement outcome is deterministic. So Bob will for sure get his, sorry, this was Y. I completely messed up the notation. So this is A, and this is X and A, and Y and B is going to be 1, and again 0. So they have the same bit. Is that clear for everyone? Okay, so that's why it works. Whenever I get a matching basis, basically I'm sure that I collapse the states to the same pair. Either they're both up or they're both down, or they're both plus or they're both minus. And now for the security. So again, let's look at the properties that I told you. So the first point is basically what I just told you. So I claim that measuring maximally mixed state in the basis of X and Z will give you the same statistics that preparing a state randomly in the basis of X and Z and then measuring them randomly in the basis of X and Z will give you. So that's what's happening. And it's because of the properties of this state, the way they look, and because when I measure, I make the state collapse, right? But also because of monogamy of entanglements now, which we heard before, if Alice and Bob are maximally entangled, then Eve cannot be maximally entangled with any of them. So it's not like Eve can also have the same sort of correlation, and when they measure, they collapse into the same thing. So how does that help with the proof? It's exactly the combination of these 2 points that leads to the fact that from the point of view of the adversary, apart from the fact that they know this is an entangled state, from the point of view of the adversary, the statistics of the protocol are exactly the same as BB84. So I don't see any difference. So if I'm the adversary and I look at all the combination of like zeros and ones that can be generated throughout this protocol, this is kind of like the same as BB84. And this is very helpful because then when I want to do the proof of BB84, I can try to first prove this protocol, which is BB92, so the entanglement-based protocol. And then I do something that we do a lot in cryptography, and that's called reduction. So you have something that you know how to prove, you have something else that you don't know how to prove, but then you can show that this is almost indistinguishable to this one. So if I prove this, I've proved that one, right? So I do a reduction. So I do a reduction to the BB84. And that's this like sort of like modern proof of QKD work. Is that clear so far? Any questions? Okay. So this might sound more complicated, like moving to the entanglement-based version might sound more complicated. And I sure had the same reaction when I saw the proof, like that kind of proof for the first time. I was like, it seems like the prefer and measure base should be easier. It doesn't make any sense. But the thing is that that's not the case. And the reason is this sort of like modern proofs of QKD. I think the nicest place you can see that proof is this paper by Marco Thomas Michel and Anthony Leverrier. And this is a really, really nice paper. First of all, it's a beast, like it's a massive paper. But what they do, and I really like about that, is that they really do a proof with no flaw. Like any assumption and anything that you can imagine that's like possible to put on the theory side in the proof of QKD, they do it. So it's like really, really rigorous, this proof. So the property of this kind of proofs that they do in this paper are this. So first of all, they do their proof based on this quantity, these information quantities that's called entropic uncertainty inequalities. So yesterday in Nana's lecture, you heard about uncertainty, right? The fact that in quantum mechanics tells you that you cannot observe x and y observable with arbitrary precision at the same time in quantum mechanics. You can look at this uncertainty from an information point of view, and then you can say, okay, so the amount of information I can extract when I'm looking at things from Z operator perspective and X operator perspective, there's a bound on them. And then you can like develop this sort of like information theoretic inequalities. So they use this kind of tools. And this will allow them to do a composable proof. Again, if you remember from yesterday, I told you that composability is it's a really nice property because it means that when I prove in these frameworks that are composable, then when I combine it with something else, I don't need to redo the proof. That comes as a guarantee. And there are, in classical cryptography, there are two main frameworks where people do composable security. One of them is called universal composability by Canetti. And the other one is called abstract cryptography. Some people might disagree, but a lot of people think, and I'm one of them, that AC is nicer when you work in quantum. So UC is a bit annoying when you want to work in quantum. So abstract cryptography is kind of like the framework. And what they do is that there are lots of works that has been done by Renato Renner especially on how to make basically how to develop these quantities that work nicely with this abstract cryptography framework. And they use basically the same sort of like structure. It's a little bit different, but it's almost the same. And again, from yesterday, if you remember, I told you that the problem with the proof that I showed you is that you cannot handle finite size key because the mutual information and these sort of like quantities we were working with, they were all asymptotic. But one thing that they do in this paper, they use, again, some tools developed by Renato Renner that are called min and max smooth entropy, smooth min and max entropy. And those quantities will allow you to handle finite size. So that's also another thing. And as I said, they capture all the possible assumptions that you can possibly capture in the theoretical level. So it's quite nice. But intuitively, like, I will not go through the proof. As I said, this is like a giant of a paper, and I don't have enough time to even like tell you all the assumptions with enough precision if I want to start. But the idea for the proof is that this sort of proofs, the reason I'm telling because it's very useful in other areas of cryptography. It's not just for QKD. And there's this idea that there's a way of proof by indistinguishability somehow. And what's the idea? The idea is that let's assume there exists a real world, an ideal world in which my functionality exists. What does that mean? So let's say I want to share a key between me and you, right? In the ideal world, we both have a key, our keys are equal, and it's perfect. It's perfectly random, right? And that's all I need to tell you what is the key sharing scheme, right? That's all. So you assume the most ideal scenario that you can, and you write down the functionality, or you draw the functionality, which is the case in AC a lot of time. You draw the functionality very precisely. You capture all the resources, all the input and outputs and everything there. So that's your ideal world. And then you have a real world where your actual protocol happens. So your actual protocol has the steps, has, do this, do that, do this first, then do this next, and all that things. And basically, an adversary interacts with the real world, right? And the idea is that if I can show that an adversary interacting with the real world, they cannot distinguish by the interaction, right? From me, that I'm looking at things from above, I know that these two are different. But if I'm an adversary, and if I interact with the real world, and I cannot distinguish what's happening in the real world with the thing that was happening in the ideal world, it means that I cannot break the scheme. So I have a security by indistinguishability, somehow, vaguely. And this is a really, really nice idea because it's a mindset shift in security proofs. It's a very different way of looking at security proof. And this is the exact way with which you can do composable security. And this is the way they do the proof of QKD here as well. So like I said, this is the ideal functionality of a key exchange. There's Alice, there's Bob, and there's a secret key that's shared between Alice and Bob, and it's exactly the same. And there's a public domain where things can leak, but in the ideal world, nothing leaks. And then what they do is that step by step of the protocol, they analyze how this resources changes, right? So for instance, they say, okay, when I do the measurement, then I produce a value of, let's say, V, and then I send it over the channel. So step by step, they capture everything that happens in the protocol. And then you can write very abstractly the whole state of the world in the ideal setting, which is like the whole state of Alice, Bob, and Eve. So everything that's there. You just like write the giant state for the ideal world. And then you can do the same thing for the real world. But now it's more complicated, right? Because you need to show that when I measure, then I do the post-processing, then I do this, then I do that, then what happens to my state? But this is doable. So they write this state very abstractly. And what they show is that these two states, now they forget about everything else in the world, and they show that these two states are very close. They're two quantum states that are very close. So it's impossible for an adversary to distinguish between them more than some probability. And if this probability is low and a state are too close, then I'm good. Then I have the security. And this is basically the idea of this like very nice and rigorous proof. Questions? Okay, cool. Yeah, that's that. So I'm going to move to other things now. If you have any questions about the QKD or the idea of the proof or things like that, that's the time to ask. Because now we're going to talk about a lot of different things. Okay, cool. You can also like find me later and ask if there's something. Okay, now I want to tell you about authentication. So you remember yesterday I told you one of the assumptions that QKD has is that I need a classical authenticator channel, right? And this seems very easy, but this is exactly the reason where a lot of like government agencies and stuff like that, like in the UK or NSA in the US, they kind of like decided to advise against deploying QKD as the main alternative for the after quantum world. And there's this like article that goes over like all the possible flaws of QKD and things like that. And one of the points that they mention, and it's quite important, is that okay, you need authentication. How on earth are you going to do that? And then Renner and Wolf, they have this rebuttal paper, which I really encourage you to read if you want to know what's going on, because it's a very nicely written paper. And they explain a bunch of things. So they're not like, and the paper is like quite nice. They're not defending QKD in that sense. They're just saying that some of these points are valid and when they're valid, and some of these points are not valid and things like that. But one of the things that they say in authentication, basically there are like 3 points that I wanted to point out to you. The first thing is that, sure, authentication is very important. We cannot say that you have it for free and like, let's go and do your QKD. It's a step that needs to be taken care of very carefully. But the second point is that, yes, so you guys are making a big deal of authentication as a problem of QKD, but you need authentication for everything. You need authentication classically as well. So it's not like QKD is the only thing that needs authentication. And the third point is that, sure, you need authentication, and we know that authentication needs something. So authentication always comes with a price. And I'm going to tell you a little bit about what options you have to do that authentication part. I'm a delay. So there are several ways you can do it. The first way you can do it is to do it by secret key methods. There are like ways in classical cryptography, like message authentication codes or MACs, where you can do authentication. Nice thing, like bad thing about it is that it's a secret key scheme. So you need a pre-shared key. You're doing QKD not to need a pre-shared key. So that's the whole point. But the good thing about it is that that pre-shared key that you need for the authentication part is not huge, right? So that's why yesterday, if you remember, I said that QKD is more like a key expansion protocol rather than key exchange or key generation protocol. And that's the reason. So you kind of start with a small key, do the authentication classically, information theoretically. And then once you've got a bunch of like bits for your new secret key from QKD, you split some of that, you put it aside for the next time you want to do QKD, and then you use the rest of it as your key. You do your one-time path. And then next time you do that, you do the same. So every time you just like take into account some parts of the key that you need to put aside to do QKD. But for the first time, you need to meet somewhere and exchange the key. And there's no way around that, right? If you want to use this scheme. Another good thing about it is that you get information theoretic security. So you combine that with a QKD, which is information theoretic, and the whole thing is now information theoretic. So it's quite nice. Another way to do it is that you can do it with public key methods. There are things in cryptography called signature schemes where people use for authentication. So you don't need an extra key for that. So this is quite nice. But they're like any public key method. So you need to rely on some assumption, and that assumption needs to be post-quantum secure for this thing to work. But now the problem is that your authentication part of the QKD becomes the weak link. So your QKD is as secure as the weakest link, which is now going to be this computational assumption. So you kind of like reduce the quality of, let's say, the security you can achieve. So now from information security, you're back to the computational security world. You still have some nice properties for QKD, which you like to do. But for that part, you would need public key. But there are scenarios in which you cannot do the first one, and you have to do the second one if you really want to do QKD. Like for instance, if you have many users and you're in a big network, it's impossible for everyone to meet and exchange the key, even if the key is small. So there are scenarios where this is the answer. And the third option, which is again not very satisfactory, but you can do it, it comes also in the Renato paper, is that you can also have a trusted third party and With that, you can do authentication. But yeah, like who we can trust for that, and that's an issue. But there are some setups in which you have a trusted third party, and then you're good. And the fourth option, which I'm going to talk about a little bit later, is that you can also use other assumptions. So now that I'm like forced to use either a key or an assumption, why do I have to use computational assumption? There are other assumptions that I can use. And I will tell you a little bit about that. But this is basically all the options you have. And you need to pick, based on your application, one of them, and then go and do your QKD or many other protocols. Yeah. So the question is that can you not use a Bell inequality violation when you have entangled state for authentication, basically? I'm not sure. I mean, you can. There are some. Let me see. I'm not sure you can do authentication necessarily with that. You can. Basically, that is a proof of quantumness. So you know that the party you're talking to has a quantum device. But adversary also can have a quantum device. So there is no reason why the adversary cannot violate the Bell inequality and Bob can.
You can check if you're actually sharing an entanglement. I mean, how does Bob doing their measurements locally and checking their...
Yeah, they can check they have an entanglement. They cannot check that. So let's say Alice wants to know that she's talking to Bob, right? She doesn't necessarily doing that knows that she's talking to Bob or to Eve, because she will know that she's sharing entanglement with someone. She doesn't know who that person is. That's why just doing that doesn't help. But if you combine that with like some other assumptions, then yes, then you can potentially turn that into an authentication scheme. Yeah. Any other questions? Okay, cool. Let's move forward. So, okay, so I told you a lot about QKD, but what is there beyond QKD? I told you there's a lot, and there's a lot. So one way you can see there's a lot of things is to go to this website called Quantum Protocol Zoo. It's a big library of all the quantum protocol. Not all the quantum protocol. This is like fairly outdated now, but it's a project that when I was a PhD student with the big team, we were working on that, and it's still live. We will soon move this to a new version, to a new basically project that is called Kagora, where we're making it much more community-based than it was before, so that people can also like upload their protocol. And the whole point is that you have a big collection of the protocol, and there is a hierarchy of structure in it, so you can see what protocols are made of, what are their assumptions, what you use them for. So it's a good way to see what are there. But I just like, and when you go, you see this like graph of how these protocols are linked. And I zoomed like just a little part of it. And you can see that the first line, the blue line, is all the functionalities you can do in quantum network. And the green line is some of the protocols. So you have things like, I don't know, anonymous transmission, Byzantine agreement, oblivious transfer, bit commitment, coin flipping, blah, blah, blah. Lots of protocols where you can do on quantum network. So go and explore that. That is fun. Here are some of the important ones. And I kind of like categorize them into a little bit of like category. So you can do things like oblivious transfer, bit commitment, and coin flipping. These in cryptography are called primitive. It means that they're like simpler functionalities which are useful in other protocols. Then you can do things that we call, if you remember in my graph of like quantum cybersecurity thing, it's called quantum enhance. It means that there are functionalities that you can also do classically, but you can do with quantum as well, and sometimes you get like a benefit. There are higher level functionalities which are related mostly to quantum computing, but they're also related to cryptography. For instance, you can do blind quantum computing, which is this idea that I'm sending my computation to a server, let's say IBM, to run, and I don't want the IBM to know what I'm running on their device. And that's called blind computing. And there are like really nice mathematical, rigorous methods which tell you how you can do that in the quantum world. Or you can verify your quantum computers and things like that. And the last part, which is I found quite like magical is that there are functionalities that are only available by quantum. So there's no classical alternative. There are things that you can only do in the quantum world. You might have heard of teleportation. This is one of them. There are things like copy protection and certified deletion that are functionalities that are like available only quantumly. So the one you see in red, I will talk a little bit about, and I will introduce you to the protocol. But this is just a little bit of the landscape. OK, you ready for the first one? Any questions? OK, quantum money. This is the first one I'm going to talk about. What is quantum money? So what is money? What is money? That's a bit of a weird question, right? Can go philosophically all the way, and you can say it's an illusion, or I don't know. So we can say it's a number that you spend, like it's just that. But like if you think about it a little bit more paranoid, like a cryptographer, you will see that not everything can be money. Like there are some properties I want from something that I would call money. So a little bit more formally, whenever you have money, you have something that's called a bank or a mint, or you can think about them like for the purpose of this talk, they're the same. And basically, this bank gives you something which is either a coin or a bill, and it has a serial number, and that's very important. Why? Because then you're going to give that coin or bill to me, and it should be verifiable. So I should know that this is actually money. This is something that I produce, because not everyone can produce money. And then the next thing you want is that you don't, if I'm malicious, you don't want me to like have a photocopying device that put one bill into it and get as many as I want. So I should not be able to reproduce money. That's kind of like against the idea of having a bank and a mint and a serial number. And so if you like aggregate these two properties, basically a money scheme needs to have two very important functionality. One is unclonability, or in classical, before quantum, this was mostly called anti-counterfeiting, or unforgettability. And the other property is verifiability. So it should be verifiable, and it should be not cloned. This is these two properties that I need for something to call money. Unless you're in the decentralized finance world, which I'm not going to talk about, so that's like a whole different scenario. But like in the normal scenarios, it's like that. All right, so because we see unclonability, it reminds us a lot to quantum, right? So like, can we use unclonability of states to create money that are nice, And one thing I should say before is that classically, nothing is really unclonable, and that's why you have to do it in like very physical, a special way. That's why when people print money, they use a special paper and a special ink and all that thing. And that kind of like ensure that not everybody can go and produce one. But in theory, there is nothing that prevents you to copy a money, right? So in theory, everything's classically clonable. But we want to see if we can get some money that's actually unclonable. And this idea was proposed by Steven Wisner, which is the same guy who did the conjugate coding. And that's why I said that he is like the person who did the conjugate coding first, because the story is that the anecdote is that he wrote the paper in 1969 and he published it later in 83. And he didn't really care about like publishing papers. He just like wrote it once and then showed it to some people. And I think it was like rejected from a conference or something. And he was like, never mind, put it in the closet. And that was it for many years. But yeah, he had this idea of quantum money. And the idea is that exactly what I told you. So let's use the idea of unclonability of a state to get money. Because that's going to be like completely physical and it's nice and based on quantum mechanics. But the hard part that, I told you have two properties. So unclonability, let's say you get for free, you need to show me the other one. So how does it work? So the money scheme works with a serial number. And here your serial number for every bill that you produce, it's a bit string. Think of like one bit of that. Basically 2 bits of that, actually. So the serial number has two parts, like x and theta. And and every 2 bits selects one state. And this is, again, exactly conjugate coding. That's why yesterday I told you if you learn that, you basically learn half of the things I'm going to tell you. So this is, again, conjugate coding. You use 0, 0 to represent 0, 0, 1 to represent 1, 1, 0 to represent plus, 1, 1 to represent minus, right? And then you just like produce a long series of bit string, you divide them by 2, you create a series of quantum state, and that is going to be your money. So this is unclonable, and you can show because I'm not in an orthogonal basis, so I have the property of unclonability. But how do I get verifiability? So the verifiability is also actually really nice because for a person who knows the serial number, they know all the bases, they can always take the state, measure in the bases that they want, and just check the bit value, right? So if I try to change that state or do something with it, then that's going to change the state, and this is going to be detected. So it's, again, the same idea, except that instead of randomly measuring and get some random bits, I'm using the bit to verify, right? So I'm using the basis to measure, I'm using the bit to verify. And that's basically the idea. Right. So, okay, is this really secure? Like, is it enough just to say that by unclonability this is secure? And yeah, you probably guessed that the answer is no. So it's no, it's not secure, so we need to show that it's secure. For instance, what is a trivial attack? The most trivial attack is that the adversary can try to guess the serial number by measuring the state, right? And of course, they will destroy the state, but similar to QKD, if they guess correctly, then they can like re-prepare the state and like pass the verification. But then here you have no information of the basis whatsoever, and you need to know the basis. This is the bit that's important for you. And if you don't know the basis, you have half probability for each of the qubits to know the basis, and this will get amplified when you have n of them. So it's half to the power n, so it's very small. It's negligible. So this is good. The trivial attack doesn't break it. Then what else you can do? Give me some ideas. Do you remember I told you yesterday that you can approximately clone? You can also do that. So you can try to approximately clone and then see if your approximate clone passes the verification. So if you do that, then you get something, you get 5/8 for every qubit. Don't ask me how I get that number. Ask me later in the break and I show you. So if you try to do approximate cloning, it's something like 5, or maybe less, something like that. And then it gets amplified over n. As far as I know, the best known attack leads to the probability 3/4 for each qubit. So that's still good if it amplifies to the end. So yeah, cool, that works. What are bad things about Wisner quantum money? So first of all, it needs private verification. What it means is that the only party that can verify your money is the bank. So you can, like, in a sense, you can only spend it with the bank, which is not ideal. Like, you want to be able to spend the money wherever you want. But there are some versions that like takes care of that. Then you can try to have quantum monies that are completely from, they're like basically public key schemes, but they're still built based on states, and they have the unclonability property. And this is still an open question. So people are working on this a lot, and this is still open. Like, public key quantum money is open. There's a lot of progress on how to do it, but they all have like very weird assumptions that people don't like and things like that. So there are good schemes. They're not good proofs for those schemes. Let's put it this way. And the last thing that makes this very nice idea very impractical is that, so you need to have a big sequence of this state, and if this is going to be money, you need to be able to keep it for a while and then spend it or verify it later, right? And the problem is that this is very impractical because you cannot like keep sequence of quantum state in their state for a long time. So they're going to decohere. They're going to, disperse, and the information will be lost. So this is quite bad. The reason this is not so much a problem in QKD, even though the states are exactly the same state that you use in QKD, is that in QKD you don't need to keep them for a very long time. You just send them and you measure, and that's it. Like you don't need to do such a thing. Okay, but it's a cute idea, to be fair, and it started like a big field of research, which is interesting. Okay, next protocol. Do you have any questions about the money scheme? No? Okay. Next protocol. The next thing I want to tell you is bit commitment. So bit commitment is a primitive. It's a very simple protocol that you can use. The reason that it is so important is that people have shown in classical cryptography that if you have bit commitment, think about this protocol as a box. If I give you that and you have that, then there's a lot of things you can do with that. So you can construct on top of bit commitment a lot of two-party functionalities. You can construct things like zero knowledge proof and like sophisticated schemes. So it's a very important two-party functionality. So how does it work? It has two phases. The first phase that's called commit phase, Alice has a safe box. You can think about it. Think of it like that. And what she wants to do is that she wants to input a bit, just a bit for now, a bit C into the safe. So it's either 0, 1, only Alice knows it. She puts it in the safe, locks the safe, and then sends the safe to Bob. Now, in the reveal phase, which is on Bob's side, Alice will send a message or something that will lead the box to reveal itself. And so Bob inputs the reveal message into the safe box. It's like the combination. You can think of it like that. And then gets the value. And it also gets a confirmation that this is it. Okay, sounds very simple. So the security properties that we want from this game is that Alice should not be able to change their mind. Right? So if I send that's why I'm sending the C inside the safe box, because the idea is that I'm sending you a bit which I cannot change later. Like I cannot lie to you and say, oh, it wasn't that, it was something else. And the second property that's on the Bob side says that Bob learns nothing about the bit before it gets revealed. And you need both of this property for this primitive to be useful inside higher level functionalities. So the first one is usually called binding, and the second one is called concealing. Okay? Yeah, so why this is important, I already told you that. So how do you do it? So this is a classical functionality, first of all. There was nothing quantum in here, right? How do you do it classically? Yeah, you can't, and that's very sad. And that's one of the no-go results in cryptography. That's quite strong. You can't do bit commitment. This is a very simple functionality. It's just that without any further assumptions, you just can't do it. Yeah, so the theorem says that it's impossible to do bit commitment information theoretically. And the reason is quite simple. I'm not showing you the full proof, but the reason behind the proof is that there are brute force attacks that works, right? So there are brute force attacks that can break the binding. There are brute force attacks that can break the concealing. They both work on both of the properties. And why I'm allowed to do brute force attack? Because I'm going for information theoretic security. So I'm allowing the dishonest parties, which in this case are Alice and Bob, to have unbounded power. So if they have unbounded power, people have shown that there's no way you can prevent them. You can't prevent Alice from changing their mind, and there's no way you can prevent Bob from looking at the bits. Okay. So how about quantum? Like surely it should help, right? Let's see. And I have a meme that I think it describes the situation really well. I let you read it. Yeah. So people were very excited when they realized they can do QKD and some very cool stuff. They were like, oh, let's do bit commitment, then we can do the whole cryptography. That's going to be very cool. And you can't. So there's an impossibility result that's been shown by Lochan and Myers that says you cannot do bit commitment even in the quantum world. So this is like a very, very strong no-go. That's not like, even quantum mechanics doesn't allow you to do that. And the intuition is quite nice, and the proof is like through the properties of like quantum information. And the idea is that there are, like very simply put, there are entangled states which I can change locally, and I can change basically my, like Alice can do, let's just think about the first property, the binding. So I can send you something, you cannot reveal it, let's say. And this state, it can correspond to two things, let's say up or down or 0, 1. But then there are local operations I can do on my side that will change the state to the other one. So Alice can always cheat, even if she cheats like locally. And this is basically an attack that makes this impossible. So yeah, so you cannot do bit commitment. But the thing is that there are ways in quantum that you can kind of like, do I have a slide about that? No. Okay, so let me tell you here before jumping to the next one. So there are ways in quantum which you can kind of like not being information theoretic in one of the properties. So let's say I want perfect binding but not perfect hiding, or the other way around. And there are some like some versions of this protocol that are still very useful, and you can do it in quantum. And this is also the reason I showed you bit commitment, even though it's impossible, is that there's a big line of research in quantum cryptography to try to do this with like assumptions using quantum. And sometimes you can do things better than you can do classically. And it's quite nice. Okay, so that was bit commitment. There's another primitive.
Just to precise, we can do bit commitment in the computational setting.
Yes, exactly. So classically, thanks. Forgot to say that classically, it's also possible to do it in the computational setting. So you can do that. All right. So another primitive that I'm going to talk about is called quantum coin flipping. What is quantum coin flipping? So you have another scenario, another game. You know, this cryptography is full of games. So now this game is this scenario. So let's say you have Alice, who is a metalhead, and you have Bob Marley on the other side. And they're going to plan for their next road trip, and they want to know who gets to pick the song for the car. And well, they have to, they cannot agree on that, so they have to flip a coin. But it's that they need to meet somewhere, and let's say Alice is here in Marseille, and Bob is far away in Scotland or in US, whatever. And they cannot just meet to flip a coin and then come back for the trip, so they have to do it over the phone, right? So they need to protocol to agree on a bit. And this is the task that Bloom, who introduced this functionality for the first time in '83, called coin flipping, or coin tossing. And this is the paper. Okay, so a bit more formally, this is the functionality that I want. So the coin flipping is that I have two players, Alice and Bob. They don't trust each other, so here the malicious parties are basically Alice and Bob, right? And they want to flip a coin, and they want to agree on a random bit, which its value is completely random, and it's known to both of the parties. And it's epsilon, so the security is characterized by how much can one of the party influence the value of the coin, right? Understand. And it's been shown that coin flipping is another protocol that is impossible to do classically. So classically, you can. It seems again like a very useful and very simple functionality, but you just cannot do it. And the statement that tells you cannot do it is that you cannot do it with a bias less than half, which means complete break, right? So you can always completely break this scheme. So I was talking to someone over lunch, was it you? Yeah, yesterday, and they actually practically did that and showed the practical impossibility of coin flipping. You know, you can talk to him next. It was fun. But yeah, so can anyone tell me why? Like, do you have any idea why this is not possible? Do you have any intuition? Does anyone have any intuition on why this is hard to do? No? So let's say I flip a coin. So let's say this is the protocol. I'm Alice. I flip a coin. So first of all, if I just like pick up a phone and tell Bob that it was head or tail, he cannot believe me because he doesn't trust me. That's simple. But let's say that I flip a coin, and then I one-time pad it. You remember one-time pad? Like I one-time pad the bit with another bit that, let's say, Bob has or something. And then I send this encoded thing. Well, if I do it, I still can't cheat. There's nothing that prevents me. So now let's say that I flip a coin, honestly, and I send it to Bob, and Bob will encode it inside a one-time pad or something like that, and he's going to basically, so let's put it this way. So let's say Alice has a random bit, Bob has a random bit. One of them will send a bit to another one, and they just XOR the bits. And this is going to be the final random bit. And by the properties of the one-time pad, I told you that if one of these values are actually random, then it's good. The bit is random. But why doesn't this work? Does anyone know? Yes?
They are not independent. You can choose both can need to be
Exactly. So the reason is that, I mean, this is just one way you could possibly do it, but the reason is that in any way you could do it because there's an asymmetry in time in this protocol. So someone needs to send an information first. And whoever sends the information first loses advantage. So the other person can see the information one way or another, and then they can cheat. So classically, there's no way you can do that. There's always someone who starts the protocol, and the person who starts the protocol loses. And that's the reason behind the impossibility. Similar to bit commitment, you can do that by computational assumption. More specifically, if you have something called one-way function, which is a very minimal assumption in cryptography, you can do this. Also, one thing you should know that you can do that if you have bit commitment. So if you can have a bit commitment scheme, out of that you can construct a coin flip. And it's not so hard to see, right? Because like if I can lock my bit inside the box such that Bob doesn't see it, and then later I reveal, then I can basically do the protocol securely. So if you have bit commitment, then you can do that as well. All right. So what about the quantum setting? So quantum coin flipping actually does exist. But the first thing you should know, let me not say it in this order. Okay, so the first quantum coin flipping was introduced in this paper by Mayers et al. In 1999. The protocol was a bit complicated, had lots of rounds and stuff, and the proof wasn't really nice. Like there was not like very rigorous proof. There was like, okay, here are these and this and this attack, and it doesn't work, and it was kind of like not so strong. Like many years later, we actually managed to completely break this protocol, surprisingly by using like variational cloning. So essentially, like you train a machine to find the best way to clone, and then by that clones, you can break this protocol completely. The reason people didn't get super excited when we broke the protocol is that no one cared about this because there were like nicer protocols afterwards, so no one really cared about the protocol being broken. But we did it as some sort of like case study of why you can do this sort of variational attacks on quantum schemes. Okay, then there was, in 2000, like 1 year later, there was another coin flipping scheme by Aharonov, and that one was nice. It has a nice security proof and everything, and it wasn't perfect, so it wasn't like Alice and Bob couldn't cheat at all. They could cheat with some probability, so the bias of the protocol for Bob was something and for Alice was something else, so it was slightly different. It was asymmetric. And again, the protocol uses some sort of conjugate basis, but not exactly plus minus 0, 1. So you need 4 states, basically 2 pairs of a state that are orthogonal, and then these 2 bases are not orthogonal, right? So they have some angle with each other. So if you have that, you can do this like coin flipping protocol. I'm not going to talk about this. I'm going to talk about another protocol which is very similar to this, but it's nicer. So it has a better bias and it's symmetric. And that's by Unbiased in 2004. Okay. Let's see how it works. So the way it works is really easy. You remember this? we're basically doing this. But I'm going to use the property of quantum state. So I'm going to use the fact that quantum state, you can encode things in them. And that's what it is. First thing is that this protocol doesn't use qubits, it uses qdits. So meaning quantum system in higher dimension. Specifically, it uses qtrits. So now instead of having 0 and 1 as your basis, you have 0, 1, and 2. Right? So 3-dimensional is fine. Nothing's wrong. And you need 4 states. So you remember in the previous protocol, in this one, I told you you need 4 states. Here also you need 4 states. But these are the 4 states you have. And basically, again, similar to what you've seen in the other protocols, one of the bits selects the basis, and the other one selects which one in that group or in that basis you're looking at. So you have 0, 1, 0, 1, plus and minus, and then you have 0, 2, and 0, 2, plus and minus in the 2 direction now, if you want to call it. And the protocol itself is that you send this, so Alice sends the state to Bob, then Bob will have to send a random bit, and then Alice reveals the A and the X to Bob so that Bob can check that if the state was what Alice claimed to be. And so then they verify, they now both have the bit of B is classical, the bit of A can be extracted by measuring the state correctly and deterministically, and so they have the matching bits. So they have a coin flip. And that's about the protocol. Do you have any questions about the protocol itself before I show you how it works? No? Okay. Cool. So it's quite easy. It's just that basically I use 2 bits to encode 1 bit, again, if you want. So I don't want Bob to see my bit. Yeah?
But then Alice is not flipping 1 coin, she's flipping 2 coins.
Yeah, sure. So Alice needs 2 random bits, but they're going to agree on 1 bit, which is this bit C, which you construct by A plus B. So the problem is not how many times you flip a coin. The problem is that they both share that flipped coin, and they both agree on that. Okay, any other questions? Yeah.
When Alice shares back A to Bob, Bob has to check that the state is actually consistent and she's not cheating, but he also knows A and B and knows if he has won or lost. So why can't he accuse Alice of cheating every time he loses, so he never loses in the end?
He can do that, but then it means that the protocol always aborts. So if Bob does such a thing, they will systematically never agree. And this is a very good question, because what you said applies in a lot of protocols. So there is this famous attack in many protocols that's called abort attack. Right? Abort attack is basically the way you make the protocol abort every time. And in many cases, you cannot prevent that. It's an attack that is there. You just assume that people are not stupid to do that all the time, repeatedly. But yeah, that's a very good point. Any other questions? Okay. So let's see how we get the bias. So first of all, for Bob, it's quite nice and easy. So let's see how Bob can bias the protocol. So if Bob wants to bias the protocol, if you remember this sort of reasoning I told you here, Bob needs to know Alice's bit. So if Bob knows Alice's bit, he can change his bit, right? So that at the end, the XOR gets the value that he wants. Okay, so Bob needs to know Alice's bit. So what is the best possible way or best possible quantum strategy for Bob to know Alice's bit? We need to do some sort of measurement, right? So you need to extract this information. And so you can, because the thing is that there are 2 bits in this protocol, but you do actually care about the bit of A. You don't, Bob cares about the bit of A. So you can write down a state that corresponds to Alice's choice of A, and a state that corresponds to Alice's choice of A equal to, 0 and A equal to 1. And if you remember yesterday, I showed you how we can use density matrices to write down a mixture of a state, and that's exactly it, right? So if I go back to here, you have all the 4 states, And you need to give me the state that corresponds to an equal mixture of A being equal 0 and equal mixture of A being equal 1. And you can do that by using density matrices like this. And then, if you remember from yesterday, there is a fundamental limit on how well you can distinguish states. And that also works for density matrices. So what is the best possible way and what is the best probability that you can distinguish between these two mixtures? Because if you distinguish between these two mixtures, you distinguish between Alice's choice, right? So that's what you need to quantify. And this is what you saw yesterday. That's called Whole-level bound. So Whole-level bound tells you that you can do that. You just need to know the distances between these two. And you actually have the description of a state. So this is like really nice and easy to calculate. I recommend that you calculate this as an exercise because this is fun. Just follow the states. I will share my slides later. Write the density matrices. You will get two big matrices. Calculate the trace distance between them. Plug it in here, and you'll see that you get the 25% thingy. And it's a very nice and easy proof. I do that always in the class when I teach that. So how about Alice? Alice's cheating strategy is a little bit more complicated because what Alice can possibly do, she can prepare whatever state she wants, right? And that's a quite powerful attack. But she will also get, like, if she prepares whatever state they want, with some probability they will get detected because Bob will measure and they will know that they didn't send the state they claim to. So there is a probability of Alice, if they don't prepare the state that they're supposed to prepare, getting caught. And this is the probability that you need to quantify. I'm not going to do that because, again, this is a little bit complicated. But what you can do is that you can basically write a symmetric density matrix that Alice is, because it's not necessarily symmetric with with respect to the choice of 0 and 1, but you can symmetrize it, and then you can show that, okay, if I send that symmetric state, then there is a probability of getting caught, and that is the average probability for the whole protocol. That's how Alice gets caught. Okay? So we saw that, and this is a nice protocol. But can we do better than 25%? Can quantum coin flipping really push this boundary more and more? And the answer is no. So interestingly, also perfectly strong quantum coin flipping is also impossible in quantum. So you can make this bias small, but not as small as you want. And actually, Kitaev has calculated, has showed how small you can make this bias. So this is the smallest bias you can achieve. So that was 25%, and the best thing is 20%. So that was actually a good protocol, and it's quite nice. But the proof for that is really hard, and it uses multiple layers of linear and semi-definite programming. So I'm not going to present it here. I don't even pretend that I know how to do the proof by heart. So that's that. But this bound is bound by Kitaev. And funny anecdote is that the reason I'm citing this paper and not the paper by Kitaev is that Kitaev never wrote this. So he presented the proof in a conference and he never wrote it. So Andrei Shayu later he wrote down that argument and put it as a proof. But it was quite fun. Okay. That is coin flipping. Another thing you need to know is that so basically in a normal coin flipping, Alice and Bob, they can call the head or tail as they want, right? So their preferred bits, they can be either 0 or 1, which is usually the case, you don't. But if you somehow determine who prefers what, so let's say I assume that Alice always prefers 0 and Bob always prefers 1. And this is a very simple modification, which makes the protocol a little bit weaker, but it's still very useful. And if you do that, it changes things quite a lot. So this is called weak coin flipping. And this is still impossible classically, information theoretically. You can do it with computational assumption. But now this time, it's been shown that you can make the bias arbitrarily small. And this was shown in 2007. But the problem is that this protocol is not a real protocol. It's more like an existence of the protocol. It's an existential proof. It's not an actual concrete protocol. And this was an open question in the field for many years, till in 2019, Atul Singh Arora solves the problem, and it's a really nice paper if you ever got interested and read that. And they design a protocol that in multiple rounds you can make this bias small, and generally this is the way to do this kind of protocol. And there's still a lot of research going on in coin flipping, so it's a quite cool topic for research as well. Okay, I think that's all I have for coin flipping. Now I'm going to talk about alternative assumption. I have quite a lot to say, so I might speed a little bit through this part. I'm not going to show you the full protocols. If we had more time at the end, or if after you got interested, you can come and talk to me and I tell you more about it. But just for now, I'm going to show you what are the other assumptions based on which you can do cryptography. So the first one, which is something I worked on quite a lot, is physical unclonability, or physical unclonable function. What is this idea? The idea is that, so we think in quantum information that the only place you can see unclonability is kind of in quantum. It's kind of not the case, at least heuristically. So people in electrical engineering, they had this idea. So basically they had these devices where it was quite unique, but when you were interacting with them, it was producing things that were unique. But then you could you could produce chips that are produced on a factory line, and they exactly look the same, but then they produce different outcome. So the way I like to think about it is more from an optical perspective. So you can imagine you have a factory line that produces crystals, and this crystal, if you look at them really closely, you see that the crystal formation is quite unique. So they're not exactly the same, but from the outside, when you look at them, they're very, very much the same. So they have all global properties that are the same and everything, but they're actually not equal. And the way you can know that they're not equal is if you shine a light to them, if you shine a light to them, you will see a scattering pattern on the LCD or on the wall. And that the scattering pattern from one to another one is very different. So if you interact with them, you will see that they're different. But if you don't, then they're very similar. And this, or the same properties for electrical circuit, you can use as some sort of fingerprint. And this is what people call physical unclonable functions. You can bring this concept into the quantum world, and you can try, you can say, okay, what do I have something like that, and can I formally define it in the quantum world? And the answer is you can, and these are unitaries or processes that are basically quantum, so they have quantum input, quantum output, but it's a physical process and you don't see inside. So the way you can think about it is almost like you have a quantum circuit, but it's not an actual quantum circuit. It's an operation. It's there is a quantum circuit inside, but you don't see it, right? But it's more like that. And one of the reasons that these are quite nice is that even things that people were thinking they're classical physical unclonable functions, like the crystals, they actually have the quantum properties because of physical properties of light. So you can study them in this quantum setting. Okay, so this is nice. Even classically, this is a really nice idea, right? So what is the problem? And the problem is that, yeah, this is a very nice idea, but in actuality, the physical unclonable functions, a lot of them, especially the classical one, they're not really secure. So how do you how do you clone a physical unclonable function? The way you do it is that think about it in a more data-driven way. So let's say you have a device, every time you interact with it, it gives you something. That something is data. So let's say you collect a lot of those data, and then you give it to the machine learning algorithm, and tell the algorithm, extract the model for me. And it will extract a model for you. Let's say the model represents some sort of function, right? Input and output, f of x. So now you have an f of x. If it's a good model of the thing that was inside, then you can produce as many of them as you want. You don't need to be able to produce the actual device, which you couldn't in the first place. But you can now, right? And it's as if you have cloned the crystal, which you could not, because even in the factory line, you could not clone the crystal because the crystal formation and everything was different. But you don't really need to, because if you extract the model, you can use the model as many times as you want. So that's how you break them. You actually break them with machine learning. And that was also historically how people broke physical unclonable functions. So the thing with the quantum version is that you can prevent that. So you can prove that you can have secure quantum physical unclonable function, provably, which is something you didn't have classically. And this is where cryptography and quantum information and learning theory, basically learnability of quantum processes, link together. And you can like formalize this functionality by saying that let's assume that this box represents a unitary, but now it's a black box unitary, and I have data of that box. So the data is like input and output to the unitary. And an adversary, they want to be able to, on a new input to reproduce the same sort of output, right? So this is a learning problem, basically. You can formalize it as a learning problem, and then you can find out how much data, let's say, you need to be able to solve this problem. That will give you a bound on how well an adversary can break that. And in the quantum setting, there are ways that you can show that you can prevent the learning, and you can have actual physical unclonability. Yeah, so unlike classical ones, these are secure. So what you can do based on this, you can basically design identification protocols. So I can give you one of these devices, and every time I want to talk to you, now I know it's you. So identification is like a lighter form of authentication. So I know every time I'm talking to you, this is you. And this is quite neat. So this is like one way of doing it. So you can design protocols based on this assumption, this functionality, that are secure, and then they're verifiable, and then you can have different versions of that. There are problems of like practical issues to this protocol. Like for instance, for these protocol, you need quantum memory, and building a real quantum POF with the properties that we want to be able to do the security, is quite challenging. I'm gonna skip through this. Yeah, I'm gonna skip through this because I want to tell you the other one as well. So the thing is that there are more relation to learning. You can have like better versions of this physical unclonable function. Then you can again show that if in certain ways you can design protocols to break them and all that, which I'm going to skip. But yeah, so the thing I will show you is that there is actually a nice practical provable way to use physical unclonability in a way that you don't need quantum memory, you don't need like a very complicated quantum device and things like that. And that again uses conjugate coding in a way. So the idea is that I use a classical POF, which I just told you that it's not secure because you can break with machine learning. But I also use quantum communication. And I do a construction which is a combination. It's a hybrid construction. It's a combination of this hardware assumption and quantum communication. So first, you build this box that, similar to the quantum money thing, when you input an X, it will give you an output, which is also a bit string. Right? So that's what classical POF gives you. So that classical bit string, you break it every 2 bits, and then you do the usual BB84 encoding. So 1 bit corresponds to the basis, the other one to the value. So you produce a stream of BB84 states. So this is going to be the outcome. And then you can design a protocol that works like this. So in a normal POF-based protocol, you just send the input, and then the person who has the POF puts the input inside the POF, get the output, and send you back the output. Now you check the output with your database, and you know that this is the good one, right? And you know that that person has the device, and you know that only that person can have the device, because by hardware assumption, this is not clonable. And that's how you do. But if you can break that POF, then this protocol is no longer secure. But this one is secure. The reason is that you're sending quantum states over the channel. So you're sending the classical string, and you use the class. So your database is still classical, but then you encode things, like I showed you here. You encode things in BB84 states, and basically every time you have a string, you only use half of them, and you send it over the channel. And then this guy will have to put that inside the POF and gets another sequence of BB84. Now they're going to send back the BB84 state, and because you have the database, you can measure and you can check with certainty if that was the correct one. The reason you use 2 parts and then you break your response into first part and second part and you combine them like this is to enhance the security, basically. Because if you only do this, you only get security against a non-adaptive adversary, and there are like some attacks here, but if you do it in this way, then you're always secure. Now, using this protocol, you can not only do identification, you can also do authentication. So this you can use as an alternative assumption to do authentication, basically, as an alternative protocol. So you could do it with MAC, you could do it with signature, public key, and now you can do it with hardware assumption. So this is like another way. Okay. So with the time I have left, I want to talk about the last topic that I want to talk about, which I think is very cool, and it's a very hot topic these days in quantum crypto and in foundations of quantum cryptography. So I wanted you to see that. Okay, so there's this idea of doing cryptography with minimal assumption. What does that mean? So in classical cryptography, it's always about assumption. Like by now, at this point in the lecture, you should believe me that this is the case. It's always about which set of assumption I pick. And people want to be as paranoid as possible so that they can prevent as much as attack as they can. And one way to do this is that you assume as least as you can, right? So you take very, very few assumptions, so the chance of them being violated gets lower and lower. And this is usually like a good practice to do cryptography. And in classical cryptography, there is basically one assumption that is like a holy grail of cryptography. Like if you have that, you have cryptography. And this is the assumption of one-way function. So one-way function means that you have a function that is easy to evaluate. So in one way, it's easy, but it's hard to revert. In the other way, it's hard, right? So for instance, factoring, you can think of it as a one-way function, at least classically. It's easy to, it's hard to factor, but it's easy to multiply and get the answer. But one-way function on its own, it's an abstract concept, right? So it's just this assumption that a function that you can evaluate in one way, it's hard to do in the other way. Like computation is hard to do in the other way. And we don't really know if that exists or not. And basically, in a world, in an imaginary world, let's say, or real world, we don't know, that P is equal to MP. In another word, there is no hard problems. There are no one-way functions. So there is no cryptography in that sense, in the classical sense, right? So if one day complexity theorists tell you or prove that P is equal to MP, cryptography as we know it in this sense is gone, right? You still have things like one-time pad, but the computational cryptography is gone. But something that's very, very interesting is that this is not the case in the quantum world. So there are assumptions that don't reduce to one-way function. And this was very surprising. And this is a quite recent result. It's by, actually it's 21. So this is a mistake, sorry. So this, I think it's 21. Yeah. So in 21, it was, so Kretschmer showed this very, very interesting result that even in an imaginary world where P is equal to MP, there are still quantum minimal assumptions that they survive. So they're not broken. And based on those, you can still do cryptography. So even in a world where classical cryptography would not exist, quantum cryptography still can exist. And this is the assumption of quantum pseudorandomness. So what is quantum pseudorandomness? Before I tell you that, I should tell you that basically in classical cryptography, based on one-way function, you construct things that are almost random, but are not exactly random. Because true randomness is almost impossible to do classically, and even like good randomness is exponentially hard. So you want tools to be able to efficient randomness that is, okay, not so good, like it's almost good, but it's efficient. And these are concepts like pseudo-random number generator, pseudo-random functions, pseudo-random permutation. And these are very useful stuff that, like a lot of things that you see in cryptography, they're built based on these things. And they all built based on the assumption that one-way function exists. right? So that's the idea. Now, what does quantum randomness mean? So first of all, you can have a quantum state and you can measure it and you get the random bits. So you can get classical randomness from quantum, but this is not what I'm talking about. Because when you say quantum randomness, a lot of people think about quantum random number generator, which is a thing, but this is not what I'm talking about. What I'm talking about is that how you get randomness over the space of states, right? And in quantum, the way to do it is through a mathematical measure called Haar measure. A good way of getting intuition about that is, so this is a block sphere, right? Let me do this quickly. Okay, so you remember that you could basically write down any state on the block sphere by this, right? Sorry, fine. Okay, so you have two angles, theta and phi, which you use to point out to things in the block sphere. So if you try to randomly, uniformly sample theta, and then randomly, uniformly sample phi, and then plot it on a block sphere, try that. This is a very fun exercise, actually. Try that using, like, I don't know, Python or something. And if you do that, if you do this, then you get this guy. So what you will see is that this is not uniformly distributed on the, even though I sampled this completely at random, this is not uniformly distributed on a sphere. It has more concentration on the poles, right? So that is not a good measure to produce uniform randomness. If you want to produce uniform randomness over a space of qubit or over Hilbert spaces or unitary groups, to be more precise, then you need to follow a Haar measure. And if you actually do that and you implement a Haar measure over a qubit, then you get a true uniform distribution. You can, there's a nice Penny Lane tutorial on how to generate Haar random states. And I really suggest you have a look at that. It's really cool. So yeah, so true randomness is by Haar measure, and it means uniform distribution over the sphere for qubits. And then you can think about the generalization. But similar to the classical, generating this kind of randomness is hard. Is exponentially hard. You need, basically, if you want to generate that over the space of n qubits, you need exponentially many gates to produce. So people have thought about ways similar to classical of approximating this randomness. And one way to do it is through a concept called T-design that sort of gives you a statistical similarity. I will not talk about that. The one I will talk about is the computational one, which is very similar to pseudo-random function. So it's been introduced in 2018 by Liu and Song. And the idea is quite simple. So they're a set of states, keyed set of states, similar to pseudo-random function, or keyed set of unitaries. And they can be generated efficiently, but computationally, they're indistinguishable to Haar measure. So I picked now Haar as my true randomness, and I say that this ensemble of states that I have that are efficient to generate, they are hard, or it's hard to distinguish them to Haar random state. So the game is like this, basically. If I give you m copies of a pseudo-random state, PRS, or if I like flip a coin, if you're in this world or if you're in another world, which I give you m copies of a Haar random state, and you're a distinguisher who is computationally bounded, you cannot distinguish between these two. And very interestingly, this is a computational version of no-cloning theorem, which was also mentioned in the original paper. And over the past 6-7 years, there's been so many interesting things just coming out of this very simple definition and this very simple idea. So this has a relationship to complexity theory, to physics, even like very crazy stuff like black holes and quantum gravity, complexity growth. So this exploded. It's a very weird and very interesting and very alive field, basically. And for us, cryptographers, one thing that's important is that you can do cryptography only based on pseudo-randomness. I'm done. One sec. So you can construct basically quantum money, bit commitment, MAC, signature, lots of things. And yeah, so basically last year there has been ways to showing that you can do that also quite efficiently. And I'm just like not gonna get into the detail. And these have also interesting relationship with the hardware assumption that I showed you before that. And if you want to see if there's only pseudo-random states and unitary in this space of minimal assumption, that's not the case. It's a big zoo. It's another zoo. It's not by us, but it's by Orsata. And you can go to this website and look at it. It's fun. There's lots of things in there, and people are still like working quite hard on this area. And I'll skip through that. And I hope you have fun.
Thank you.